Thank you. So I'm Fred. I'm here today to present our work on threat intelligence computing on behalf of Xiaokuai and my other co-authors who could not attend the conference. Basically, threat intelligence computing is this new methodology to help with facilitating cyber threat hunting tasks. So to get started, let's try to define what cyber threat hunting means. And basically, this proactively and iterative process of formulating and validating threat hypotheses based on security relevant observations, data, events, and also domain knowledge. So if you think about your typical security operation center, usually you have your first and second line incident responders, and then you have your third line incident responder with expert security analysts, which usually are handling the cases where your standard security defenses, security posture cannot handle. So they are looking for the stealthy attacks, the attacks that are concealed in your environment, basically. The process goes like this. You start with observations, events, threat intelligence. You formulate different threat hypotheses, and you design your own analytics. They use different tools and techniques that goes from statistical analysis to machine learning and so forth to validate those hypotheses. And this is an iterative process, so it goes because usually we're talking about multi-hop, multi-step attack chains until you eventually confirm those hypotheses and you're able to write a report saying, hey, this is how it happened. So conventionally, our threat discovery approaches, they depart from our capabilities. So we have monitored data from many heterogeneous data sources, and we have also sources of alerts and intrusions, and also threat intelligence like anomaly scores, indicators of compromise that get factored in this data. And then the threat hunters are faced with this challenging task of basically coping with this heterogeneity and write their own analytics, so to speak, to parse and sift through this data and visualize it in an attempt to connect the dots and find where the malicious attack campaign, uncovered attack campaign that is hidden in the data. So the problem is that in addition to being slow and ad hoc in a way, it's almost like an artful work because those analysts, they have to cope with campaigns that also can change on the fly. So they have to cope with this idea of dynamic reasoning, dynamic threat hunting, because this takes sometimes days, weeks, and as we know, there's too many attack vectors and too many. The space for moving within an organization is very, very, very large, and correspondingly, we're going to have a number of different threat hypotheses to cope with different ways of attacking and exploiting our environments. So. And that's not to say about the human capital, right? No machine automated task can actually capture that opaque expert knowledge that are in the heads of those analysts. It's very scarce talent, but they are the ones connecting the dots, using the different tools, and they make sense of them. So in this work, we've proposed this idea of being able to compute on top of threat intelligence. So the key idea here is to recast threat hunting, the task of hunting for threats, as this temporal graph computation problem. So the key insight is that this brings a unique homogeneous representation that kind of takes care of that heterogeneity of our different sources of data. So to give you an example, let's start with, for example, this host level computational graph that we depict here. So we have, for example, this Node.js server that receives an inbound connection from a remote endpoint, and then handles that connection to a worker process that handles the session. And that happens again and again. And eventually, there is an attempted connection that basically hijacks that process into spawning a bash shell, which then reads from some sensitive source and communicates with a third-party server to exchange some information. So the task here is then, how can we take this new way of recording computations, this computational graph, this temporal computational graph, and uncover this kind of patterns? So that's the task that we give now to the threat hunter. He wants to somehow program these things on top of those computational graphs to be able to uncover step by step the big picture, the broader attack campaign. So the approach is basically this: converting threat discovery into this computation on top of CGs, which basically eliminates data heterogeneity. By providing this uniform representation, then we can capture behavior and alerts at different levels of granularity, as I'm going to show you, from process level, host to network level. But also, by means of giving and providing this data representation, now we can have a single operational approach on top of it, which basically reduces to writing patterns that are matched against those computational graphs. So it's a different way of thinking about the problem. So just to explain what this representation mean more concretely, we have entities that have durations, and they are scattered across your space dimension. We have events that are point-in-time events that occur during the computational history. And then you have labels. So this is a labeled computational graph. So basically what this allows us is to provide different label algebras, basically different semantics that the analyst, the threat hunter, can leverage to perform different types of analysis. So this makes up the computational graph. And basically, this gives us this canvases or mini canvases that allows us to model different, basically, types of computation. So at the process level, you can think about, for example, functions and function calls being your entities and events. At the host level, you have your processes and files and system calls. And then at the network level, maybe your endpoint resources and the link layer, the communication that net flows between those endpoints. So to take, for example, the case of the host level computational graph, your entities would be then the subjects, like the process threads, and objects like files, pipes, and sockets that you have. And your events would be the system calls. But most importantly, you can have labels. So I mentioned, right, you can incorporate into this reasoning process metadata on top of those entities and events. So those could be, indicators of compromise that your enterprise has learned, or user behavior analytics, or even, your anomaly scores. So that also informs, that's threat intelligence that informs the analyst. In addition to that, remember that I mentioned that this is an iterative process. So the ability to label intermediate steps of computation is also important because it can inform the second and the subsequent steps of that reasoning procedure. And finally, of course, you have element attributes, which are also modeled as labels in this graph computational platform, which allows us to define attributes of your entities and events, things like processes, command lines, IPs, and whatever and whatnot. So talking about the operational abstraction. So it's really executing cyber threat hunting by means of matching patterns on top of your computational graph. So for example, very simple example, starting from observation. What if you wanted to ask, what are all the network activities that your node process had in the past, right? So you have this history of your computation. So the task would reduce to basically define this simple graph pattern that has a node being an inbound connection from a remote endpoint. And this is how we would model in our platform. Basically, the platform provides a new language, a domain-specific language called tau calculus. And that language basically allows the threat hunter to define, for example, a node entity that has two constraints, two predicate expressions. So the type of that node, of that element, of that entity is of type process, and the command line includes a substring named node. The other entity that you define them is, for example, a network resource that is of type network, and then you define a flow, an event that connects the two. Symmetrically, you can also define the outbound connection. And with these two patterns, what do you do in our platform? You basically create a hyper pattern, like one that combines the two. And basically then you would yield, a traversal on top of our computational graph. I'm going to explain more how it works. It's a distributed graph data store, but it's going to retrieve all the entities and events that match that pattern. Well, a little bit more complex. Let's go into the threat hunting task proper. So say that you would like to model the example that I just described to you on the Node.js spawning a process that then executes the data to a command and control server. So how would you go by if you wanted to do that? So basically, you have to come up with some sort of description of that behavior. And the description is a graph pattern again, but you don't have to model that pattern, like the complex pattern from top down. What you can do is basically understand what you want and then build the pattern piece by piece So, for example, you would basically abstract the idea of a two-hop level spawning of a process. Then you would add to that another pattern, for example, that constrains that spawning come from your server, the Node.js server. Maybe another pattern that look at your list of sensitive files, maybe a dictionary list that you have and maintain separately as a label as well, that tells which files contain sensitive files. So that's like a data exfiltration pattern into a process being read by a process. And then finally, maybe a pattern that describes some sort of command and control behavior. Maybe you have from your threat intelligence, open source threat intelligence, you know that IP is associated with a command and control server, and then you can describe that pattern as well. And the idea is that our platform will provide the traversal for you. You don't have to implement those algorithms again. Basically, you plug them into those smart built-in traversal primitives that will basically combine those patterns and execute that pattern matching for you. So in this case, for example, just to give a taste on how this constraint solving works, because that's essentially what's going to happen, we start solving, well, there's lots of heuristics that goes on, but very simply, we solve constraint by step. So first we solve the first constraint, and we have all the entities that match the Node.js process. Then we solve the second constraint, and now we constrain the space. So we have to go back and see in all the entities that match the first constraint, which ones have the inbound connection from the remote host, and we do that recursively, right, successfully. And until you get to that, satisfiable subset that basically satisfies that pattern. So the way this is implemented in our platform, basically during the parsing of the patterns that it's implemented in the talk calculus language, we attach to the abstract syntax tree this accessory data structure, the graph of constraints, that basically denormalizes the constraint relations as entities or nodes in that graph. And basically the problem of constraint satisfiability here becomes, again, a traversal, a recursive traversal in this graph. So we have to go back, because every time you solve a step of the constraint, the state changes, so we have to go back and prune unsatisfiable constraints. So the algorithm is described in the paper, so I'm not going to spend too much time here. But I wanted to give you an understanding, or a glimpse of what this talk calculus platform is. First, I start with the language. So I have already showed some snippet of code showing that it's a declarative domain-specific language. Very simple. There are other constructs, the full semantics, syntax, and type checking rules are all in the paper, but there are also function declarations, variable declarations. I mean, you can look at the paper. Very important is that it supports composable pattern matching, which is not something that many graph computation languages can support, and has temporal and information flow primitives built in addition to that graph current traversal support that I just showed you, like the constraint satisfiability. On top of that, there is the platform proper, which basically comes at the front end with this iterative shell and graph visualization tools that allows the threat hunter to visualize the results of each step of the threat hunting process. There's also an interpreter and compilation toolchain, and as I mentioned, we have the built-in algorithms, the constraint solver, and also user-defined functions that can be linked and built upon. So there are external interfaces, for example, where you need, for example, other sorts of computational models that can be linked into this graph computational platform via this external interfaces that we provide. Very important is the distributed graph database. Implements multi-level caching. It's distributed across many nodes. And two important things is that during the ingestion of the data, it keeps replica sets to enforce temporal locality and also topological locality. I think I missed the sound here, but can you all hear me? Yes. So temporal locality. So that's important because that will actually tremendously expedite data retrieval later on. So that's the part I was explaining. And the reason why we chose to build talk calculus and not reuse Titan or Neo4j and other graph computational platforms that we have available is really the reason for scalability that I was mentioning. Also the fact that the other languages or platforms don't allow for immutability. And this is very important if you're talking about computational history. So we enforce as well, there's no side effects. I mean, during the processing computation, we don't change the graph representations. Also, I already talked about the pattern matching, and of course, the different ways we can index and retrieve the data for performance. So, how many minutes I have? 5. Okay, so I'm going to just skip a little bit over this and show you a little bit a glimpse of the code generation part. Of course, we have type checking, all those things. But in terms of code generation, if you look, for example, at this constraint predicate here, that's basically saying that these two entities are connected in a graph. And those two entities, if you think about the typing rules, X could be an entity, Y could be an event, or vice versa, right? But an entity couldn't be connected to an entity directly. It had to be connected to an event. So if you look at the first column, you have an event that connects to an entity. That's the constraint, the predicate. And then you have different ways or, physical locations where those events and entities, those X and Y, would be located in either in memory or on disk. And depending on where they are located, the compiler will optimize and decide on which strategy to code the query to query that entity and event. So there are queries to optimize for temporal locality when you get event by an entity, or they're the ones optimized by space locality, topological locality, entity by ID, or if you have things cached in memory, then you just process things in memory. I already talked about the graph ingestion part. It's important to notice that we keep things aligned in disk, so that usually when you fetch the blocks, they're all consecutive blocks, and as well like for pages in memory. So just talking a little bit about performance. I didn't mention that, but this project is inserted in the context of a DARPA transparent computing program. So all the data and evaluation that was performed was realized in the context of this DARPA program. So there was a 2-week competition last year where red teams attacked the systems, generated data. There were about, I think, 6 systems with different 4 operating systems and collected data. And basically we had amassed 160 gigabytes of data with 6 monitor hosts. And just to show the performance benefits of temporal localities that we keep in the database, look here at different time slices. We wrote patterns to fetch all events within 60, 300, 600 seconds, and so on. And on average, the retrieval rate of all the millions of events that we had, they were about 0.5 seconds. So that's actually really, really good. We were leading team in the competition. And then as well for describing, for example, topological locality that I was describing for. So they use this notion of UUIDs that is basically obeys this RFC form 122. And it's very hard to define a notion of locality for those UUIDs. They're really random and they have no correlation. But still, because the way we ingest and we keep the replica sets, we can still achieve fairly good performance, as you can see here, about half a second for 128 elements with all the labels. So because each query for a UID actually yields many, many, many other queries for labels and other things that are associated with an entity. Just an overview of the case studies. There was a war room, basically a 2-week experiment with red teams attacking those systems with attacks that were unknown to the defender team, and also that basically were tested to bypass existing anomaly detectors and malware analysis tools and so forth. So different OSs, all events coming and entities coming from those collected and ingested into our graph data store. And basically, the attacks that we were able to detect were from reflective DLL injections, things like double pulsar that were used in conjunction with Eternal Blue, all the way down to download and execute behavior from a browser, right? And our completion rate, after we got the ground truth, we learned that we were able to detect about 67% of the attacks that were actually exposed in that data. So to conclude, with this work, there's a lot to talk about. A lot that maybe I don't even have the the technical depth to talk about in terms of the graph database. There was a work of a fairly large team of researchers, but basically we introduced this new methodology called threat intelligence computing that basically solves these two problems. The first problem is that it eliminates the heterogeneity of data representations with our threat hunters are faced today. And second, it provides this uniform programming environment for threat hunters actually to reason about the threat hunting steps. So if you will, that actually enables this human-machine attack detection strategy co-development. As they work their threat hunting steps, that domain knowledge that they have in their hands gets encoded into those patterns and those programs that they specifically write to detect further and bigger patterns. And we showed Tau Calculus as this platform and showed that it achieves excellent performance for the challenge that we were faced with. Thank you.
Yeah. Hi, thanks a lot for a great talk. So yeah, I think this is really great. And actually, I'm trying to digest the new concept, right. But I try to have two questions. One is clarification question, and another thing is more kind of the generalization of the approach. First of all, I want to see compare your approach with some existing solutions like alert or the monitoring integration system. What I can come across right now is a Splunk-like CM solutions.
Yeah.
So what is the jump that you are making from those kind of solutions? That is one question. The second thing is that a lot of movement that I see from the industry is that they are trying to come up with a threat exchange like a standard, like a sticks or those kind of things. Whether were you thinking of integrating your framework with those kind of the information sources so that you can even automate and like accelerate the process? Yeah. Yes.
Two great questions. To the first one, you're talking about the new SIEM systems, the ones new detectors that we have that gather from different data sources and are able to raise alerts, right? So the scope of this project is really past that. Assuming that you already have those systems in place and are issuing, raising alerts and everything, this just become new threat intelligence, metadata for this work. We are really talking about, things that go undetected. So that's this is basically what threat hunting is. It's trying to uncover things that are concealed, and stealthy in the middle of the.
Still trying to understand the scope of the input to your system.
Right.
Is it so things are already detected, but somehow the signals are buried in the noise, and so you can pull that out via this analysis?
Right.
So it doesn't help you if you haven't detected it via a sensor. It's just stuff that's detected, but there's too much data for the human to actually pour through. Is that making connections? So I apologize if this is a rudimentary question, but I just want to understand the scope of the project.
Definitely, I think it's a great question. It's I think all of that and more, right? It's this ability also to cope with heterogeneity of your data sources. So being able to also encode and transduce domain knowledge expertise into an analytics that can be ported across. That's another aspect of our work, right? But what you said is also true. We are talking about a computational recording that has been already recorded, a computational history, right? But many times what we see is that attack campaigns, they take many days, or if not months.
Or years, right?
Or years, right? And it takes many, many, many days to discover them. So the idea is that by having this kind of code reuse, if you will, and model reuse, if you will, we would be able to get quicker and faster to those breaches and attack campaigns.
All right, thank you.
Right.
One quick question about, if I understand this correctly, this is a way to analyze an event graph, generally speaking, right?
Yeah, a labeled temporal event graph.
Right. Okay. I'm wondering what happens if there are events missing. Let's say
that's a great question. We addressed that in the paper. Yes, this is an open problem. We didn't tackle this yet. This is an ongoing research, and that's true for I think almost everything. So being able to reason and doing, for example, pattern matching on disconnected, event chains, for example, that's something. Yeah, definitely an open question.
Thanks.
All right, let's thank the speaker.